Good day, everyone. Today we are looking at chi-square. Okay, what can we use chi-square for and what can we not use it for? So the name chi-square involves more than just one test. Usually we hear people say, I want to do a chi-square test, chi-square test. But that is all there is to it that we know. However, in the statistical sense, when you talk of chi-square, you will have to mention the full name because there are three tests that we can do with this single formula. Okay, so without putting this in context, it becomes hard to tell exactly what hypothesis to test if you are asked to do so, unless you know all these three and you are able to distinguish given a data set. All right, so the three tests that use the same chi-square test statistic, they also use the same formula. Okay, the name that we give to all of these three also use the same formula. However, the interpretations are slightly different. So all of the three tests are categorical variables but answer different research questions. That is true. So the values put into the formula come from different places as well. So we will see we are going to have an example of just two of them. The other one we want because we are here to treat regression analysis and it's kind of linked to it. So the general shape of the chi-square distribution is skewed to the right. Okay, it is skewed to the right. So we will have something like this, then it is something like that. Okay, so that is the chi-square distribution, and that is what we mean by it is skewed to the right. So the exact shape which affects the p-value associated with each each value of the test statistic is determined by the degrees of freedom. Okay, so you have the chi-square, the degrees of freedom, and then the alpha value. So this is what we use to determine what table value to read. So the three tests that I just mentioned are the goodness of fit test, the test of homogeneity, and the test of independence. So the first and the last one is what we will have the examples on. Okay, for the second one, when we deal with regression analysis, we'll see how that is applied in that sense. Assumptions. Whether we are going to do the test for the first, second, or third, we need all these assumptions before we go ahead to do that. So one, both variables are categorical. So in the case of the test, the contingency table, the row variable and the column variable should all be categorical. For the goodness of faith, we only need one variable and a hypothesized value. So whether two or one, all should be categorical. And all observations are independent. So you can see that this is taking the same shape as in the analysis of variance. So the independence of your sample is key. So we need to know how was the sample taken, how was the data collected. Okay, cells in the contingency table are mutually exclusive. You do not have an overlapping something. So for example, if you are given if you want to draw a table, let's like this, and this is age group, and you decide to label them in this manner, 5 to 10. Now you cannot have here 10 to 15. Why? Because there is an overlap. So that is what we are talking about here. So all of them should be mutually exclusive. There shouldn't be a case where somebody will be confused about where to put a particular value. All right. So expected value of the cells should be 5 or greater in at least 80% of the cells. Again, let's draw a contingency table, 2 by 2 table. Okay, A, B, C, D. So all these are the cells we are talking about. So 80% of these cells should not contain a value that is less than 5. So if it is 5 or greater, that is good. The chi-square can give you an estimated value, and your results will be correct. But if it is less than that, it is not able to give you correct results. So how do we check the assumptions in this case? In the analysis of variance, we did check how to check these assumptions. So same way here, let's see how we are going to check the assumptions for the chi-square statistic. Okay, so checking to ensure that both variables are categorical is pretty much easy. You can tell once they are grouped, you know, they are in categories. Once you have, let's say, Ghana, Nigeria becoming column names, then that is categorical. Once you have, let's say, primary school, JSS, it becomes categorical. So you can simply see from the divisions that, okay, these are grouped in this manner and it should be categorical. So the only way to the independence assumption, the only way we can check this independence assumption again is to verify that each individual included in the data set was surveyed independently. So we talked about randomized design. Yes. So you should have a randomized design. Then if the data is collected through that means, then we can say that independence assumption is satisfied. Otherwise, we'll put a question mark on that. So if we use a random sampling method, like any of the ones we know, simple random sampling, stratified sampling, systematic, all those ones, yes, they are probability samples, and we expect that our observations will be independent as much as possible. So it can be verified easily that the cells are mutually exclusive. If it is in ranges, you can simply tell once you have something like this, 6 to 10 and so on, then you can tell that yes, if a person has a value of 5, you know where to put that person. If a person has a value of 6, you know where to put that person. But then if you are going to have this 5 to 10 in that order, then a person who has the 5 will we will have a problem placing this person. Some people might just place it in between the 0 and 5 category. Another person will carry it forward to the 5 to 10. So whichever one that you're going to use, that is going to be conflicting. Okay, another person too can choose to just put, after all, 5 is in both categories, so I'll put it here and put it there. That is wrong. So once you have something like this, then we can say that they are not mutually exclusive, and therefore we cannot apply the chi-square analysis. Now we can use the formula, the row sum. Okay, the row sum multiplied by the column sum over the table sum to calculate the values of the expected values for each cell in the contingency table. So we will see that in an example when we are going to the test of independence section. Okay, for now, this is how we can check the assumptions and satisfy them or not satisfy them. This is the test statistic for all of them. Okay, this is the test statistic that will be used to test for the three tests under the chi-square distribution. So the first one, the OI, are the observed, okay, observed values. The EIs are the expected. So the one expected values. And the expected values are gotten from the row sum multiplied by column sum all over the table sum. Okay, this is how we calculate the expected values for each of the cells. Okay, all right, so let's move on. Goodness of fit, the first one. So the goodness of fit is used to determine whether or not a categorical variable follows a hypothesized distribution. So let's say it was said that students for the past years, students in quantitative methods class never had, or their average score was always 50. So this is a hypothesized value. if you are now coming to do the test yourself or to do the experiment yourself, you give a test to this all the students doing quantitative methods, then you take the results and do the analysis to see whether what they are saying is true, that the average value or average score for students in quantitative methods or any other course, if you choose to, is equals to 50. Okay, so this is where we use the chi-square goodness of fit. Okay, so in other words, we are looking at do the set of values of this variable fit a specified distribution. So if you're going to say that the results of a particular course follows a particular pattern, you would want to see whether or not this is true by taking data to do the analysis. And again, we are going to use the chi-square goodness of fit for such tests. This gets confusing because specified distribution in question is not the chi-square distribution of the test statistic. So when we say we want to see whether the variable follows a specified distribution, we are not looking at this distribution that I drew earlier on, the one that is left skewed. It could be any other. So we want to see whether or not the the values that we have, the data that we have, follows that particular distribution. And we have to come and use this goodness of it to do that particular test. Okay, so yes, it can be a little confusing when you're trying to explain to another person. Rather, you may be testing whether a categorical variable has a uniform, that is equal distribution across all categories. Okay, and that is the 50. So you have the x values. So let's say you have 10, 20, 5, and you want to see whether or not the mean is 15. So you have uniformly distributed hypothesized value across all of them, and this is the chi-square goodness of test. So we would expect the frequency of each category to be equal. Exactly. Okay, and that is how we can do this particular test. The chi-square goodness of fit test uses the following null and alternative hypothesis. Remember, we said the three of them, they are answering different research questions. So this is the research question that the goodness of fit is testing. And the null is that a variable follows a hypothesized distribution. So the scores in an English exam is equals to, let's say, 85. This is hypothesized, and the scores here are the mean of the scores. Mean of the scores is coming from your data set. Okay, so you want to see this mean that we are getting from the data set, is it statistically equals to the hypothesis value of 85. Alternative is that a variable does not follow a hypothesized distribution. So this exam score that we are trying to check, it actually did not come any closer to 85. So the mean of the scores of that particular exam that we have taken is nowhere close to 85. Okay, either it is less than that or it is more than that. So there is a difference. Example. So let's take an example of the sort. So lecturers were asked to record. So in terms of taking attendance, lecturers were asked to record the number of students in class on a daily basis. So it is expected that equal number of students come to class every day if all registered students of the class were present and attending classes. Okay, now the unfortunate thing is that we cannot get an equal number every day in the class. Why? Because probably some will come today and will not come tomorrow, but majority will come to class. Okay, so that difference, we agree that it will be there, but is that difference big enough to say that it is not uniform? Okay, so the following are the records taken by, so we have from Monday to Friday. These are the records that were taken: 50, 60, 40, 47, and 53. Okay, so we will follow the steps in solving this question appropriately. Okay, so first step is to perform the goodness of fit test using the hypothesis, and yes, state them first. So how do we state the hypothesis? An equal number of customers come into the shop each day. Okay, all right, I think I used an example and I tried to change it to something that would make us actually um, understand. Okay, so this should have been that we have equal number of students coming to class. Okay, not customers. Equal number of students coming to class each day in the week. Okay, or we can say that all registered students come to class every day. So all registered come to class every day. So the attendance record that we have taken, it's going to that's what we're going to use to actually test and see whether or not it's true that they all come to class or they don't come to class. Step 2, we calculate the statistic. This for each day. So for Monday we have 50, we observe 50, and the hypothesized value will be 50. Why 50? Now see, when we add up the numbers, we get from Monday to Friday, add them up, and we had 250. So 250 divided by 5 will give us the 50. So this is going to be distributed uniformly to all the days of the week. Okay, so that is why we have the 50, 50, 50, 50 throughout. Okay, so as the formula above is indicating, we subtract the expected value from the observed value, square it, and divide it by expected value. So this can be confusing. Once it's a square, it doesn't matter if E comes first before O, all over E. You still get the same answer because once it is squared, the negative value is going to vanish. Okay, so we basically will have the same answer. So we do the same for all the days and take note of the final answer. Okay, this is 0, this is 2, this is 2, this is 0 0.18, 0 0.18. So that is what we are going to add together and call it the chi-square statistic. Yes, so this is what we just picked out from there, add them up, and we have 4.36. So 4.36 is the chi-square statistic. Okay, now the critical value of the chi-square distribution with 4 degrees of freedom. So we can indicate that as 4, 0.05. That is at 5% degrees, 5% confidence significance level. Then we have 9.49. Okay, we are going to compare the 4.36 with this 9.49. Okay, what will be the decision rule? If this what we have calculated is less than what we read from the table, then we do not have enough evidence to reject the null hypothesis. However, if that value were to be greater than what we read from the table, then we have enough evidence to reject the null hypothesis. Okay, so now since the test statistic calculated, looking at them, is less than the critical value, we say that we don't have enough statistical evidence to reject the null hypothesis. Therefore, management do not have enough basis to say that the class attendance is not equal at all times. So that is to say, everyone comes to class, all registered students come to class for that particular course. Okay, so the second one is chi-square test of independence. How do we perform a chi-square test of independence? Okay, and what is it in the first place? So this is where you have the contingency tables, and if you look at the hypothesis, this is talking about two variables are independent. But when we looked at the goodness of fit, that wasn't the case. We want to see whether a set of data follows a particular hypothesis value. But here we are looking at two variables are independent, and the alternative says they are not independent. So if they are not independent, it means there is some kind of association between them. There is a relation between them. Okay, so that is the next test that we're going to look at. So for example, we have this data where we have student male and female, and then we have a School of Applied Science and Art. We just call that Science, Business, and Engineering. So basically, we want to see whether male and female attending to this or doing, is there a relationship, in short? Okay, gender and then the type of courses that they do. If you want to um, categorize the courses that they do into the sciences, the business, and engineering, is there any statistical reason to say that these two are kind of related? If you are a man, you are likely to go into the sciences than if you are a female. Can we make statements like these? Okay, all right. So that is the um, data that we have. Now we need to do the calculation. How do we do this calculation? This is where the row sum and then the column sum comes into play. Okay, so let's say from here and from here. So these totals is what we calculated from there. So for example, if we want the expected value for male science, that is the first cell, what we do is we take the row sum of that one, 260, multiply that by the column sum, that is 210, and divide that by the overall total, 500. Okay, so if we do this calculation, we should be getting 109.2. Okay, again, let's take here 20. Where the 20 is, how do we get the expected value for that? So we can get the expected value of that by considering the row total for that one and the column total, including the overall total. Okay, so let me try using another pen to indicate that. So this is the next calculation. Okay, and we still need this one to be added there. So that will give us 240, multiply that by 65 and divide it by 500. So do the mathematics again and we will end up with 31.2. Okay, so that is what we call the expected value. So we will need to draw a table and put them inside. Now what I like to do is to write the pair them. Okay, I would pair them so that the next stage of the calculations can be done without any problem. Now first of all, we need our hypothesis. Gender and program of study are independent, and the alternative will say gender and program of study are not independent. So the first one says they don't have a relation. The second one says they do have a relation. Okay, so let's go ahead and do the calculation and see whether or not we can go with the first hypothesis or we have to go with the second hypothesis. Definitely, we will have to choose one. All right, so let me have, say, the column for what? I am not just going to draw the same table again. So I put it as observed and then expected, so that now the observed are the values we had before, 120, 95, 45. So this is the male and the female we had 90, 130, and then 20. So this is the female part. Okay, now expected values, if we do what I showed you earlier, then we can just do that and populate here. Okay, expected values 109.2, the second is 117, and the third is 33.8 for the male. Then the female row, we're going to have 100.8. Those are expected values, 108, and then 31.2. Okay, now the good thing is that if we are going to add like the row totals and the column totals, if we decide to add only the expected value, we should have the same totals as the observed value. So if you do that and you don't get the same total score, then you know that you have made a little mistake somewhere. Okay, now the next stage of the calculation is to have our O minus E, square that and divide it by E. Okay, that is the next one we do, and we do this for all of them. So it means that for the first one, I'm going to have 120 minus 109.2, square that and divided by 102.2. So if we do this, we are going to have 1.07 according to my calculator. Now the second one the same way, 95 minus 117, square that and divided by 117, and this again should give us something like say 4.14. So if we're going to do this for all of them, let me populate it so that you try your hands and see whether we are getting the same answers. So for the first row, we just did that calculation, 1.07, 4.14, 3.71, 1.16, 4.48, and 4.39. I've already done this part of the calculation, so I know that I have the values for it. All right, so that is not all. We need to sum this up. Okay, so just sum them up, all these, sum, and that will give us the chi-square statistic. Okay, so we sum all that, we should have 18.95. So our chi-square statistic is equals to 18.95. Okay, so that is how we do the calculations for a chi-square goodness of fit. Now, chi-square test of homogeneity. This one we won't do any calculation here. Basically, we will need it somewhere in the regression line. So the difference is pretty much the same. Okay, but the difference is that this one has a clear independent variable. Okay, that is the population groups. Okay, and then we have a clear dependent variable. So when we get to regression analysis, this is where we talk about test of homogeneity. But for here, we just have to mention it so that we can differentiate between the three types of tests that we can have using the same chi-square statistic. Okay, all right, so based on this, I think that is we'll end it here, and then the next we'll look at Yates correction. Thank you and have a blessed